in a standing wave, we have a situation that looks something like this. Okay, a standing wave, let's say a second harmonic. The wave comes out to here, then it inverts and comes back to here, and you have this back and forth motion that you're familiar with. The amplitude of motion of a point at a position x is going to be determined by the sine function for that wavelength. Okay, here's a full wave, so at position x the amplitude will be the magnitude of some maximum amplitude, which we call ASW. So ASW is the amplitude of the standing wave. It's the amplitude of an antinode. Okay, ASW times the sine of kx. Now the sine of kx, k is just the wave number, is just the function that gives you the shape spread out over the length of the string. So sine kx is just this function that we've graphed here. If we multiply the maximum amplitude, which is the amplitude of this graph, by the sine of kx, we get the amplitude for a given point. So that now we see that this point is moving back and forth with this amplitude and angular frequency omega, so that we take this amplitude, which is ASW sine kx, multiplied by the cosine of omega t. That's just amplitude times cosine of omega t for this point. Again, this is the amplitude for this point. We multiply the amplitude by the cosine of omega t, and we've got an equation of the simple harmonic motion. Let's note that there's no energy transfer in this wave. There's energy in this wave, but once the wave is set up, there's no new string vibrating. The string is vibrating as it is, so there's no energy transfer here. So that the standing wave just maintains its constant energy until energy begins to get dissipated, of course. And that happens. But in a situation we have no dissipation, we're going to say that the standing wave maintains its energy and has this form.